Hi, welcome to AB Video 5.4b, more derivatives and integrals of natural exponential functions. Okay, so we're just moving on with more applications. There's not really any more formulas in here. Find an equation of the tangent line to the function at the given point. Here's your function, here's your point. Obviously, I need a point for a line. I also need a derivative, which is the slope. I'll need to take the derivative of this. Now be careful, this is just a constant. So you have e cubed times, and the derivative of ln x is 1 over x, so it becomes e cubed over x. I need the slope at x equals 1, so if I replace x by 1, my slope is e cubed, and that's the end of that question. Use implicit differentiation to find dy dx. So what I've got is e to the power of x times y, there's your product rule, plus x squared minus y squared equals 10. So I take d dx of each side because I'm looking for dy dx. So what I have is I have e to the xy. Remember, the derivative of e to the thing is e to a thing times the derivative of the thing. Well, the derivative of this thing is a product rule, so I'll need parentheses. So I have the first factor x times the derivative of the second factor, which is 1 dy dx, plus the second factor, which is y, over times the derivative of the first factor, which is 1. And then plus 2x, and then minus 2y dy dx, because it's implicit, equals 0. Okay, so I'm going to distribute through. I'm going to have e to the xy times x times dy dx, plus, and then e to the xy times y, plus 2x minus 2y dy dx. They asked you to find dy dx, so you're going to have to gather the dy dx's on the left and the non-dy dx is on the right. So you can see how that's going to become minus y e to the xy minus 2x, and then you'll factor these dy dx's out. You'll be left with x e to the xy minus 2y. So you'll divide the other side by that. Find an equation of the tangent line once again, so more of the same, okay? So we have a point, we need the slope, which is dy dx, so we're going to take the derivative. This is the ln of x times y. Remember, use your log properties. So now we're going to take the derivative, that's 0 plus 1 over x plus 1 over y dy dx equals e to the power times the derivative of that power, which will be 1 plus dy dx. So we're trying to find this at the point where x is equal to 1. So, and of course I need to know, and y is equal to 1. So I replace the x's by 1s, the y's by 1s, 1 minus 1, and I will end up with 1 plus dy dx equals e to the 0, which is 1 minus dy dx, and then you have to take it from there. So you end up bringing the dy dx's to one side, the non-dy dx's to the other side. You'll find out that the slope is 0, which means it's a horizontal line, which means it's the line y equals 1 because it goes through the point 1, 1. Find the extra points of inflection of x times e to the negative x. So domains all real numbers. This is a product rule going on here, x times e to the negative x, so first term times derivative of the second, which is e to its power times the derivative of its power, plus the second function, e to the negative x times x, the derivative of x, which is 1. Now, I can factor out the common factor of e to the negative x and get negative x plus 1. And I could even rewrite it as negative 1 minus x over e to the x. Now, that's my first derivative. My critical numbers are whatever makes my first derivative 0 or undefined. It'll be 0 when x equals 1. It'll be undefined never, because e to the x is never undefined. So you take a number line, you put your one and only critical number on it, which is 1. And now we're going to have concave up, concave down. Well, if I plug in a number, first of all, e to any power is going to be positive. Remember, a positive to any power. So it all has to do with the numerator. If I plug in, let's say 0, I'll have 0 plus 1 is positive. Whereas if I plug in 2, I'll have negative 2 plus 1 is negative. Okay, so we do have a relative max because it goes from increasing to decreasing. It happens at x equals 1, but you would have to plug 1 back into here and get 1 times e to the negative 1, which is 1 over e. Now they also wanted points of inflection, so we're going to need the second derivative. So here's my first derivative right here. Well, I'm going to use a quotient rule. So I have denominator squared. I have denominator times derivative of numerator minus numerator times the derivative of the denominator. So I'll factor out the e to the x. That'll give me x minus 2 inside here. And the e to the x will reduce with the e to the 2x, right? Think of it as x minus 2x, which is negative x. Therefore, it's 1 over e to the x. Okay, so here's my second derivative. When is it 0 at x equals 2? When does it not exist? It doesn't ever not exist. It's always equal to something. So I place my only crucial number on my number line, which is 2. I plug in a number less than it and greater than it to see what happens to the second derivative. Well, it's right here. Denominator is always positive. So if you have 3, let's say you pick 3, 3 minus 2 is positive. If you had negative 5, it's always a possibility. Sorry, if you have negative 5, you'll get negative 7 over a positive, which will give you a negative. And therefore, since there is a change in concavity, I have a point of inflection. Remember, the way to get the y coordinate is to plug it back into the original f of x function. So if I take 2, I get 2 times e to the negative 2, or 2 over e squared. Okay, so find the indefinite integral. So again, when you have x's in your exponent, most likely you'll let u equal the exponent. So you let u equal the negative x to the fourth, which gives negative 4x cubed dx as its du, which is exactly what they gave you. So this is just integrate u to the u du, which is e to the u plus c, which is e to the negative x to the fourth plus c. Next example, you're going to let u equal the exponent, which is 1 over x squared, better known as x to the negative 2. The derivative of that is negative 2 times x to the negative 3 dx, which becomes negative 2 over x cubed dx. Okay, so coming back over here, I need negative 2 over x cubed dx for my du. Well, I've got the dx and I've got the over x cubed. The only thing I'm missing is that negative 2 right here, which I can multiply in and counteract with negative a half. So now we have negative a half the integral of e to the u. Remember, we let u equal 1 over x squared, and we just know that this is the du, and therefore we have negative a half e to the u plus c, which is negative a half e to the 1 plus x squared plus c in this case. Okay, this is kind of the degree of the top is bigger than the degree of the bottom, so you can split it up. E to the 2x over e to the x plus 2e to the x over e to the x plus 1 over e to the x, giving you e to the x. 2x minus x is x. Here gives you 2. I'm sorry, over here gives you 2. And then 1 over e to the x is e to the negative x. So now you can integrate e to the x, you get e to the x. Integrate 2, you get 2 dx. Integrate e to the negative x, you get e to the negative x, which I'm showing down here. You would let kind of u equal this negative x. The derivative would be negative dx. You'd have to introduce the negative and counteract. So that's where I end up with the minus e to the negative x plus c. Number 116, you have the ln of e to the 2x minus 1. Well, what happens is that's just 2x minus 1 because the ln of e to a power, an ln is e to which power is the question mark gives e to this power. So I guess that's what it is. So I let u equal the exponent. Sorry, I replace ln of e to the 2x minus 1 by what it's equal to, which is 2x minus 1, and then I easily integrate that. Evaluate the definite integral now. So now we're going to go to the definite integral. Again, you're going to let u equal the exponent. The derivative of that, isn't that nice, is 3/2 x squared dx. Well, I've already got the x squared. I've got the dx. The only thing I'm missing is the 3/2. So I need the 3/2. I introduce the 3/2. I counteract with 2/3. And now you have 2/3 e to the u sorry, I have 2/3, and then I'm integrating e to the u, and this whole thing was du. My integral of e to the u du is e to the u. My u over here was x cubed over 2. Notice how I pulled the 2/3 on the outside. Just I find that easier. We're evaluating that from -2 to 0. Plug in the 0. You do not get 2 or -2. You get 1. And then minus, and then replace the variable by -2. So -2 cubed is -8 over 2 is -4, and e to the -4 is e to the 4th power. And then 1 minus e to the 4th is the 4th power. Whoops, sorry. Okay. So we have e to the, we're plugging in 0, so we got e to the 0. Notice how I left the 2/3 on the outside. Replace x by -2. -2 cubed is -8 divided by 2 is -4. E to the -4 is 1 over e to the 4th. E to the 0, don't forget, is 1. So you have 2/3, and I just found a common denominator. Here's another example. This time there's no point in letting u equal the exponent, because letting u equals x does nothing. This time we're going back to something we knew already before, which is let u equal the denominator. The derivative of that denominator is e to the x, -1 times e to the x dx. So the only thing we're missing is the negative. Introduce, counteract. I now have negative the integral of 1 over u, and that is my du, which will give negative ln of absolute value of u. But you can't leave it there, because u is 5 minus e to the x, and you're looking for an actual value. So you have to plug in the 0 to 1 before you sell this property. So you'll plug in 1, you'll get ln of 5 minus e. There's a minus out here. And then minus, you'll plug in 0, and you'll get 5 minus e to the 0, which is 5 minus 1, which is 4, and the absolute value of 4 is 4.